Hello, let's talk about transformers and PanelBoards and other elements that are used to stop and allow the flow of current and for security purposes so that the load is not active and the voltage is contained into the system until you want to use it. And we want to know how fuses, we want to know how breakers and transformers are used to transport and control the flow of electricity. The goals are to be able to determine and decipher, understand the type of transformers used in small and large equipment. We want to be able to conceptualize the physical behavior of transformers, how they work, and we want to be able to characterize the transformers losses or how are they designed for an application. Evidently, we are not going to learn all the content for going into designing the transformer, but we do want to be able to understand how they work, how to size them, which transformer is not intuitive or build an intuition of which transformer should not be used for a certain application. So first of all, we want to make sure that we understand that transformers are designed for very specific voltage outputs and for very specific voltage inputs. In other words, if a transformer is designed for a voltage input of 120 volts and a voltage output of 12 volts, you should not be connecting the transformer to 240 or 440 volts because it's going to create a problem. So the first thing we want to remember is that transformers are mainly used to manipulate voltages for equipment, for machines, for applications. In some cases, because of the size of the building, because of the age, sometimes the building is pretty old and the electrical connections are not up to the current standards, the voltage is a little less than what is required, and that is very common. So the transformer uses 120 volts AC, and the building supplies 108, 110 volts to that particular side of the building because of losses, inefficiencies, size of wires, etc., not being up standard connections. Whatever it is, there's something called the buck and boost controller or transformer where you can step up the voltage to be able to use it in your application. So transformers can do both things, either step down the voltage, hence 120 volts to 12 volts, or step up, say 108, 110 volts to 130 volts. Transformers are 100% enclosed so that you don't have access to the high current or the high voltage that goes through them. If you notice the transformers that are next to your house or your apartment complex, they get wet when it rains, they get temperature, they get sun very hot because of the sun, they get very cold when it's wintertime. So they're completely enclosed because the cover, the casing, is what is touching the environment. Inside is completely sealed. Where do you find transformers? In most of any electromechanical systems. Anytime you have AC to DC or AC to AC applications, or DC to AC applications sometimes, anytime you want to manipulate voltage, you would find a transformer. So next to your house, you find a transformer to step down the voltage to your house. Because remember that high voltage is easier to transport, it's easier to distribute So the transformer will bring it down to what you need at your house, 120 to 40, whatever it is. In a dishwasher, you need transformers for the 120, for instance, that you get from your wall, from your in your house. The control board of that dishwasher is probably going to use 12 volts or 24 volts. Transformers will be present to bring that voltage down. Washing machines, motor controls, etc. There are different types of transformers. One of them is the dry type. The dry type is what you would find in a dishwasher because it's enclosed, right? The dishwasher uses water and high temperature steam, obviously high temperature water, but that is inside the casing. You don't have those going to the electronics. In a refrigerator, you have a transformer in the control board that is also a dry type. Dry type are the ones that are enclosed, and we'll see pictures and figures in a little bit. The enclosed part of the coils are dry, which is the part that is doing all the electromagnetic uh, performance and all the electromagnetic behavior that the voltage can step down given the number of turns that the coil has. We'll see that in a minute. The dry type transformers have no liquids to cool it down. It's just convection by air. Space around coils dissipate heat. So the designers build a transformer such that there's space for the heat to be dissipated because as you know, the current, the electricity, the materials are used that let flow of current also get warm depending on the performance, depending on the temperature of the system, depending on how long it's running, etc. There's a protective metal enclosure to be able to connect to ground. So there are some safety features that are part of the transformer, and if those features are not present, you should not install the transformer. Sometimes people start removing things because they don't fit. That's obviously a bad design of your enclosure if you cannot fit your transformer in your system. That it's very important that's completely sealed and the enclosures are intact because those enclosures are connected to ground. And there are different installation options. They're on the floor, they're on the ceiling, they're outdoors like the one by your house, they're in the control panel, they're etc. It's just the design, the engineer and the operator decide where to plug to connect the transformer that is hopefully nearby the inside, hopefully it's inside the panel board and nearby other high voltage elements. So we talked about the buck and boost, and that's a little different than the control transformers. The buck and boost are usually larger. Of course, they have to bring voltage up, so they need more coils from one side to the other to be able to increase the current and the voltage. But both are considered small transformers. So they're the size of a fist sometimes. They don't need to be extremely large when they're dry. The dry type transformers don't need to be very big. They also raise the voltage by a small percentage. So as I said before, if the voltage coming into your building is 108 volts, but you need 130, you can use a buck and boost controller. Or a buck and boost transformer, I'm sorry. So this is a drawing, this is a figure showing how the transformers operate. So you have your inputs, your positive lead and your negative lead. You have your ground on the very bottom. Let's see if I can find out. Yes, so this is where you connect your positive lead. This is where you connect your negative lead. Remember that AC current, voltage and current, usually by standard you have leg 1 and leg 2 and neutral, right? So if you were to show your plug, this is your plug and this is the wire. There's little one, there's another one, and there's another one on the very back. So the one that forms the triangle, if you were to see like that, is your plug. This round is neutral. The white one and the black one are L1 and L2. And some drawings, they are called Y and X and G. Okay, so I'm sure you've seen that before. But the point is that you connect L1 and L2 to your transformer leg. Neutral will be connected to ground, obviously. And this ground is from the transformer ground. And then we'll see in a little bit that the one side of the transformer, we'll see in a little bit that one side has the coil, and then there's an electromagnetism, there's an electromagnetism physical behavior here, where this material in the middle has all the magnetic and electrical development of currents and voltages, and then it goes like the over here is the second part of the transformer. So this is voltage 1 and this will be voltage 2. We'll see that more in detail, but you have to be careful. It's very easy to connect one side of the transformer. This is what comes from your wall, 120, etc. But usually transformers have other places to connect the output, and that is because sometimes they're designed for more than one application. So if you connect this and that, they could be 12 volts, or if you connect, say, this leg to that leg, that could be 24, etc. So you have to be careful when you use a transformer and read the drawing to see where you need to connect your motor or your system. So in this example, I'm connecting 120 volts AC and I'm getting 12 volts AC out for a motor or for a sensor, etc. There's another type of transformer called isolation transformer, and those are the characteristics are that no connection between the primary and secondary windings exist. So that's what we just saw, and there's just no physical connection between the two windings. It's an electromagnetic field. They usually have some type of electrical noise, so you can hear them working. You can hear when they're, because of their frequencies and their parts, and they require separate circuits. They're similar to dry type transformers, and they have the same number of coils in the primary and secondary winding. So isolation transformers are often used for reducing the noise of a voltage input. Remember that transformers, the operating principle of transformers is induction, and this is because of the magnetic field formed between from the coils. And in the particular case for an isolation transformer, since there's no connection between primary and secondary windings, the voltage in many cases stays the same, but it's filtered, or the signal is able to be more neat, less noisy, so that it could be used for better applications. So you will commonly see that the primary and secondary windings have the same number of coils. Remember, if you vary the number of coils, you're varying the electromagnetic field on each side. Therefore, the voltage or the electric field could be less or larger depending on the number of coils and the relationship between one side and the other. But for isolation transformers, the number of coils in the primary and secondary windings are usually the same, precisely to keep the voltage the same, but work on the noise from the signal input in the system. So this is an example where, as you see, the windings, and the windings are this copper, these are the windings on each side. But the useful part of this is that if you have your voltage coming in at 60 hertz or 120 volts, 60 hertz, this is frequency equals 60 hertz. The voltage will remain the same, and the frequency will remain the same, but the noise is filtered out. And this is because of the magnetic field formed inside the conductive material being able to clear the voltage. Now, this is not necessarily a filter like the one that you have in your radio or the one that you use for signal processing, because those are different types of signals. Those are usually signals that, like my voice in the time domain, would be having a bunch of different peaks, and then if you have to filter something out, then you usually filter amplitudes and filter frequencies. This is just the noise within the signal at a very specific frequency. You can filter it with an isolation transformer. Why would you need this? Well, because sometimes to operate machinery and operate systems, you need a very defined voltage input. If you start having all these issues, then you have less efficiency, you have less power because of all this noise. You can get system to operate in a different state that you don't want it. So sometimes these isolation transformers come within your compressor, within your pump, within your system, precisely to be able to get your signal in a less noisy shape. So to recap, the size of the transformer depends on the load on the circuit. Sometimes you know beforehand what type of signal you're getting. Sometimes it takes building the system and iterating within different configurations of transformers to make sure that you have the most optimal performance. And sometimes some disturbances are expected, sometimes some noise or disturbance or a type of disturbance is noise. So in other words, sometimes noise would be not expected and shows up given the configuration that the system requires, or given the operational loads on a building, making the system less efficient. So once things start working, you also get to test your system, make sure that it's working as you expected, and to make sure that your transformer is as efficient as you want it to be, there's something called the K factor. And that is a rating that gives you an amount of efficiency, and is given by the following expressions. When we talk about transformer losses, we have a type of loss given by the core. So if you remember, for instance, in the isolation transformer, you have a core where your coils are connected to, and there's some loss because of these materials not 100% able to carry out all the current. There's just some small resistance. Even though the materials are conductor, you still have a small resistance there. And there's some loss given by the load. And the total loss is the combination of the loss because of the load and the loss because of the material or the core. And the losses are due to the voltage excitation of the core. So on one hand, the material is not 100% able to conduct all the electricity, and on the other hand, there are some intrinsic losses by transferring current through it. It gets warm, gets less efficient because of the temperature differences, etc. Another thing that I want to mention is that the I squared times R loss is given by something called the eddy current. And eddy currents are when you have a piece of material and you have a magnetic field inside. Depending on the geometry factors on the edges, you would have some build of curls or some build of eddy currents. Basically, that's the name. Where eddy currents are a type of loss where the energy is not transferred, it's not distributed, but instead is creating a vortex of a field there. So like if this is a fluid, it will create a spiral or a vortex. So those things also happen in magnetism, and those are called eddy currents. And there are a type of laws that also contribute to the material being less efficient. So if you were to show that mathematically, sometimes you would not probably, you won't see this part if you are only trying to get a transformer to install it on an application. But for those companies that design transformers, this is pretty much what they have to work on, which by the way, we're not going to be experts on this part, but I do want us to know how they are designed so that we have an idea of how transformers need to operate based on their design. So the total loss is given by I squared times R. This is the current through the transformer. This is the resistance of the material. We saw that this is the eddy current loss, which this is found mathematically or modeling or experimentally. And this is other types of loads because of connections and soldering, etc. This eddy current loss, people have PhD dissertations and research and plenty of analysis on how to compute this stuff. And for us, we're just gonna mention a few things because, as I said, people get their whole careers on studying eddy losses or eddy currents in magnetic fields. But I just want to mention that it's very cool for those of you who like math because it has to do with something called harmonics. So if a magnetic field is traveling at a certain frequency, remember that the magnetic field and the electric field are connected by 90 degrees. So if the wave of electric field is going parallel to the screen, the electric field is going perpendicular to it. So electric field and magnetic field. Both fields are connected. That's why transformers can use the inductive principle to operate, because by changing the magnetic field, you can change the electric field. But harmonics are these frequencies that create resonant behavior in materials. So when you have this magnetic electromagnetic field going to a material, so right now assume this is air, and they start, they hit materials with some random shape. Depending on the frequency that the electromagnetic, which is not 60 hertz anymore, because we're saying that we're going to add coils and we're going to add windings, etc. So this frequency, which could be pretty high, kilohertz, megahertz, etc. We'll see later on that we can go up to gigahertz, kind of like a cell phone signal. When this magnetic field hits a material, depending on the size between atoms and depending on the size of the atoms, because one thing is if this is gold, and one different thing if this is silicone. So the size between the atoms is going to be different. There's going to be some resonance, some excitation within it. If this frequency has a particular magnitude, a particular size, it could hit a resonant frequency in this material where things start to vibrate at the same time, and it could break it or it could let it through very fast. So in other words, what I'm getting at is that these harmonic frequencies are very interesting, and you'll see this in physics a lot because this is one of the most interesting things really in nature when you add mechanical or electromagnetic frequency with a material. So if you want, you can look into harmonic impact if you play instruments. I'm sure you've heard this. Those are the frequencies that having different having different frequencies, they can still build on top of each other. For electromagnetics, it could be that you break a material. For acoustics, it could be that it sounds uh, more dense, etc. But the point I'm trying to make here is that you can compute the eddy currents based on different factors, such as the harmonics and the currents going through the core. People who build transformers use these quantities to determine the amount of loss, okay? And with the amount of loss, you can find the K factor, which is what we were trying to find. So it's a very complicated expression. Of course, I'm not going to ask you to compute the K factor of a transformer, but I want you to know that there are ways, very complicated really. There are different methods to compute the K factor, which this is one of them, where you have the ratio of fundamental frequencies, which fundamental frequencies are the frequencies at which you have resonant behavior, and you have eddy current, you have the currents within the transformer, and of course you have a summation of all the frequencies going into the all the harmonics going into the system. So it's a pretty cool mathematical expression. But when you go to buy a transformer, they're gonna give you a chart with voltage, current, K factor. Okay, so obviously you want this K factor to be, again, this is something that is based on people who build transformers, but the point is that if you use a transformer that is say you're using it for an application that the current is bigger than what it's supposed to be rated at, then if your transformer still works, it's going to be less efficient. And the reason is because it's not in the envelope of the K factor that it was designed for. So this is an example also about how to determine the the magnetic flux through the transformer. And say in this particular case, N1 could be different than N2, or they could be the same if they're an isolation transformer. But the point is that you can try and find the flux density by the voltage from the first winding. This is the magnitude of the voltage coming into the first winding, divided by the number of coils or the number of turns on the primary core times sine of omega t. So remember, omega is 2 pi frequency times the time. So if you want to find the magnetic field in 60 seconds, or if you want to find it in 5 hours. We saw before that this expression is from the electromagnetics on two coils near each other, so where this is N1 and this is N2. This phi is the magnetic flux density of the magnetism going through a material. So this is the primary, this is the secondary side. Here would be your motor, your compressor, your whatever it is. It could be a pump, etc. And the point of this transformer here, if n equals n, if n1 equals n2, then remember that you're trying to get the signal in a less noisy state. If n greater than n2, it's because you're trying to step down. And if n1 is greater than is less than n2, it's because this is a buck and boost transformer. Another type of transformer is the oil-filled transformer. And it's called oil-filled because instead of being a dry type transformer, it has oil or a fluid, like a non-polar fluid, inside the transformer to cool down the windings. So the key here is that it has a fluid. So let's see if I can write that. Yes, fluid to cool down, so for temperature purposes. This fluid has to be non-polar, because if the fluid is polar, kind of like water, you can create a pretty nasty electrical hazard because the coils are carrying high voltage, high current, or basically carrying electricity. So the non-polar fluid will not interact with the electric field, but it would help cooling the windings. Now they have these fins outside, and this is because of the heat transfer principles. If you look at on your computer, the board, the what is it? The processor has these fans where are used to maximize the surface area so that the airflow can cool down the equipment. So the engine on a motorcycle, you'll notice that they have the shape, they have fins on the front and back or different parts of the engine so that when the motorcycle is moving, air cools down that through the fins. In other words, if you have a material that is warming up, then you can add fins. This is a heat transfer theory that you can add fins, and of course they're the same material. That's why they're using some aluminum or some very conductive material, so that if you cool down these fins, then that will transfer the cold temperature, or the less hot temperature will be transferring to the rest of the system that is warming up. So that's why you have these cool, or that's why you have these fins to cool down the system. These transformers are often, usually, placed outside because they need to be big for the fins and because of the amount of oil they use, and also for security reasons because they usually use high voltage, and because they need some special connections to operate. So for instance, if you notice, they're usually the picture doesn't show it, but they're usually on top of a raised bed or a concrete bed that um, instead of just the ground, so that they can be isolated somewhat from the ground. In order to characterize a transformer, we usually use kilovolt ampere, which is a unit simplified as kVA. We by now should know how to compute kilowatt hours, which is an important unit to be able to determine the amount of energy that we use. But the unit used for the amount of power, or the amount of the size of the transformer, is usually kVA, kilovolt ampere. The K, the kilo, stands for 1,000. V is the voltage of the system, or for the system to operate, and amps is the current through the system. So if we want to find the kVA of a single-phase transformer, the single-phase transformer only requires operating voltage, the amperage going through the voltage, divided by 1,000. So 120 times 10 amps divided by 1,000, that would be a way of computing a kVA unit, or the kVA, the kilovolt amperage of a transformer for a single phase operation. For a three-phase transformer, is the voltage times the amperage times 1.73, which this is a factor based on the three phases going into the transformer, divided by 1,000. The 1,000 is the same because the 1,000 is because of the kilovolts. For one phase is just voltage times amperage. For three phase is V times A times the 1.73. The 1.73 again is because of this the square root of 3 that comes from computing the 3 phases going into the transformer. So for example, if you're operating 120 volts AC and the amperage drawn is 200 amps, which is a lot, the way to compute your kilovolt amperage is by multiplying 120 times 200 divided by 1000. That gives you 24 kVA. Now there are standards, and that's something that you can find on the booklets of manufacturers or even online. This is the actual amount, the net amount of power that the transformer is using, but the standard size is 25 kilovolt amperage. So if beforehand you do the calculations and you get that it's 24 kVA, when you buy the transformer, you go to the tables and you buy the next standard size, which is 25 kVA. Now the connections are pretty important. This is first of all for safety reasons, so make sure that you have your connections always correct, and also for performance issues, because if they're loose you don't have all the current that you would need, therefore you have less efficient systems based on loose connections. Another key factor to making sure that the transformer has the right connections, the right size gauge wire, the right size endings, that is soldered or clamped correctly, is because of the vibrations induced by the magnetic fields. So as you can hear, sometimes transformers could be pretty loud when you're nearby. That's the magnetic field is creating some vibrations that are usually big enough to lose the connections if they're not soldered or connected properly. You have to remember that loose connections can heat up and damage the transformer, because when they get loose, they have less contact area to transfer the current, which is usually high current, and it could be a hazard. So again, connections are extremely important. If you remember, the wires, the connections are conducting materials, so they have to get maintenance on them to make sure they are free of corrosion and they have no dirt, because dirt has particles, molecules that could be conductive and can damage or create corrosion spots on the connections. And usually this is good for transformers or any system. Follow the recommendations provided by the manufacturers about how to maintain, how to install, how to operate. Now, in case of the three-phase transformer, which a lot of electromechanical systems have three-phase systems because of the amount of power that they can carry, because three-phase systems have a lot of beneficial aspects, kind of like controllability. You can control motors that are three-phase much more efficiently than one phase, because you can use the phases to meter the motor. So one example of how to calculate the kVA for a three-phase transformer is exactly the same. You find the voltage, you use the amperage draw, and you find your kVA, knowing that you multiply your V times your A times 1.73, or square root of 3, it's easier to remember, divided by 1000. And in this particular case, voltage is 208, the current is 260 amperage, and or 360 amps, and multiply it times square root of 3. Divided by 1000, that gives us 129.5 kVA. If you look on the tables that you can find online or by manufacturer, the next standard transformer for a three-phase application is 150 kVA. So you go one size up, and in this particular occasion, for this particular application, you use 150 kVA. If, on the other hand, you go to a plant or go to a system, go to an equipment, and they're already having a transformer in place and they already have everything set up, and you have to characterize the system, or you need to find out what's the amperage for maintenance, or if you're changing a wire, if you're changing a part, if you're changing a transformer or a fuse, you can also do that by just reversing the formula. Before, we were using the formula to find the size of the transformer if you're designing the application. If you're mounting the system for a particular setup and you're designing the control panel, you choose the transformer. In this case, for example, they're calling you to provide maintenance on application. Then what you need to do is check the voltage, which that it's usually provided by the system because motors tell you the operating voltage. So that is a good rule of thumb. See what's the voltage going into the system by the transformer, or if it's plugged into a regular wall socket, or the plant will have drawings about the voltage going into the systems. So you use that voltage. If it's a single phase, you know that you don't need to use the square root of 3 at all. You just have the value of the transformer, which in this case they're telling us that a 100 kVA transformer is installed. So if you want to find the amperage, you just divide your kVA, it's 100 times 1000 because you want the voltage and amperage. You have to get rid of the kilo part, the kilo VA. So this is times 1000, and you say divided 120. That will give you 833 amps. 120 is the incoming voltage. So this 120 VAC is the same voltage that you get at your house. This is not necessarily a lot of voltage, but this is a lot of current. So in your house, you will get maximum 30 amps. That's how the sockets and the wires and the breakers and everything is designed to operate for safety reasons. So this obviously is an industrial application where the amperage is going all the way to 833 amps, which is a lot. So in other words, this 100 kV transformer allows you to use 133 amps at 120 volts. For three-phase is exactly the same, except for now you have to use the square root of 3 or the 1.73 factor. Say the example says that you have a kVA transformer with a voltage of 208 volts, three-phase. Calculate the maximum amperage. So we know that 25 kVA is 25,000 volts amperage. And if you want to find the amperage, you simply do VA divided by 173 divided by voltage. This is the VA from the transformer. This is the transformer part. So we're doing 25,000 volt amperage divided by square root of 3 divided by the voltage incoming to or incoming voltage, the one from the line going into the building or to your system, and that gives you an amperage of 69.47 amps. So this is the voltage that your system is drawing. Sorry, not the voltage. This is the current, the amperage that your system is drawing. Now let's talk about one of the most important parts of any setup, any electromechanical setup. It's the panel board and switchboards. These are the hardware components that control and provide safety for your equipment. So a rule of thumb is that electricity must be set up from large values to small values. So for instance, it's coming to the building at 440 and then step down to 120, or Then from 120 you need an application where a motor is operating at 12 volts, so you step further to you go down to 12 volts. So that's the rule of thumb, because it's easier to transport electricity at higher voltage than a lower voltage. So the main use of panel boards is for safety and controlling reasons, because you can always use tag out lock to provide maintenance, to switch off the whole energy, the whole system while you change parts. This is where the loads are located. So you have a main part where everything is occurring, and then your energy is transferred to the systems throughout your work, throughout your company, throughout your factory, whatever you're using this for controlling or for operating machinery. And you have switchboards where you're gonna have different types of loads and equipment installed. So in other words, if you have an application where you're using a compressor at 240 volts, and you have a motor at 120 volts, and you have a pump at 24 volts, all this is volts AC. Then say you're having a line with 440 volts AC going to your building, then a transformer outside of the building, or it could be much higher actually. And we're talking about single phase right now, just for simplicity. Single phase. Then 140 volt transformer is installed to step down 240, and from 240 you connect your compressor, and then actually this could be a refrigerator. So you're bringing 240 to 240. 240 is going through your whole building, through your whole factory, through your manufacturing line, and you're connecting your compressor at 240. Then the same system, which is a refrigerator, we're saying, has an input of 240. Inside, you have a transformer to step down to 120 to have a motor for rotating the doors or for rotating whatever needs to be rotated inside. Common refrigerators don't have a motor, but we're having an example where we have a custom refrigerator with a motor operating on 120 volts. Or I don't know why it couldn't be at 240, but this is the example. It's operating on 120 volts. And then we need a switch for creating ice or to open a gate or a door or something, which is operating at 24. Oh, a pump. We said we have a pump to push water at 24 volts. So we have another transformer to give us 24 volts. So your voltage is stepping down using transformers. This is a very common practice. So a panel board usually looks like this. You have, in this picture, you're gonna see that we have all these parts where this is your incoming power. In our example, we had 240 volts. And then we can either here have fuses and breakers, probably very common to have relays, and then we distribute to all the other things that we need. So say this is one side of the building where we have manufacturing. This is another side when we have offices, but offices use 120, so there's a transformer here. And then this is for, I don't know, for the parking lot, so this is also gonna be a 240. So this is the control board, which is designed to be organized by sections. Okay, now here we're gonna go wires and different things to exit the control board. So obviously there's gonna be wires enclosed in some type of enclosure to let the electricity flow. But you usually organize your electricity loads in groups of similar loads. So that would be pretty hard to service if you combine which happens, and it's sadly not very useful because usually this is one reason why there are so many accidents, because people don't follow standards in many cases, um, where they have the same control panel for everything, where they need to within the control panel organize their loads um, in different sections. So when you go into a factory, you'll see very often different control panels. You can have several control panels. One is for, say, power from manufacturing, and the other one is for offices, and the other one is for lighting the building, etc. So, and they're usually posts carrying the wires throughout the company, but it's not a good idea to combine everything within the same control box. So this is one example. We have the incoming power going into the system. Then we have the terminals taking the power into different breakers, where the breakers control different sides of the building and different sides of the equipment. Could be like if equipment needs, if we have different machines connected in parallel, or from a same energy source, then we would have ways to shut down machines from a breaker box. There's a circuit breaker to shut down the whole power into the building, so that, and usually this has a lock, so you can place a lock where whenever you're servicing any machines, you lock this and turn off the power input. So this is extremely important, because when you're operating, when you are servicing machines, the electricity has to be locked into the panel has to be locked, and the unit can be serviced with no chances of having electricity going through the system, because you don't want the unit to start while you're operating, you don't want the electricity flowing while you're changing a fuse, etc. Then outgoing terminals are conducting materials, or other relays or elements that allow the electricity to flow out of the control panel into the rest of the system. So panel boards are used both for single phase or three phase. They're a common element for safety and control reasons. They have electrical interior, they have breakers, they have fuses, relays, etc. Inside, they use bars. Sometimes when they have high voltage, they use bars to conduct the electricity. So it is very important to have access to the whole control box and be able to switch on and off the power depending on the type of maintenance that you're providing. So if you're doing maintenance on the box, the switch obviously has to be off. The control panel has to be without any voltage or current going through it. And then you can change the wires and connectors and terminals, etc. So it is very important that you have access to a control box for maintenance that has no power. Usually panel boards and control boards use high amperage loads, which, remember, the amperage is what really harms you. The voltage is dangerous, of course, but what truthfully causes injuries is the amperage. So remember to be careful with panel boards. Never service a panel board that is not under tag out, which tag out is a standard by OSHA, where there is a tag with the signature of a manager or a signature of an operator, a certified technician, that is saying that the panel board is going to be out of commission, so that you can provide maintenance on it. Never work on a panel board that is not under tag out conditions. Panel boards are used for commercial, for institutional purposes, industrial applications, So in commercial buildings and schools and factories, etc., you will find one of those almost everywhere. For current protection, because you know if you have all your systems running and all your lights on, then more current is going to be used. So you need to have a way to control your current, and those are usually with breakers and fuses, sometimes with relays. And this is because conductors have a maximal electrical load. This is called the breakdown load. And overloading conductors can generate heat. That's why you can see smoke and you can see explosions sometimes of transformers. Circuit breakers and fuses protect the circuit. So in a control box and in a panel board, you would have breakers and fuses connected throughout the system to protect the flow of electricity. But again, never work on a panel board unless the panel board is under tag out conditions. So one thing is to turn the breakers on and off if this is okay, but a completely different thing is to swap a breaker. That only should happen once the control board is off. So breakers have different parts. One part is the housing, also called frame, which is made of an a dielectric or insulator material. So insulators. And this a plastic or some type of polymer. And this is because you don't want electricity to flow through the casing. This is an inductor or dielectric material, oh, not an inductor, sorry, an insulator or dielectric material. And the purpose is to have a sturdy or safe housing that has no electricity going around it, because you can see this particular breaker can operate 240 volts and 30 amps. If more than 30 amps go through this breaker, then the breaker will flip. And this is designed to withstand short circuits, so it's an element of used for safety and precaution, and can insulate and isolate circuits. So once you're drawing more current than the design current, this breaker will shut off and it will isolate the circuit for protection purposes. Another important part is, we mentioned this already, is the contacts and the connections. This is a crucial part because in the contacts and connections are a lot of the failures found in electromechanical systems, because you need certain amount of current flowing through the elements, and if the contacts are only contacting half or say 20% of the area that they're supposed to be contacting, there's going to be a spike of current on a very small area, and that is going to cause a breakdown current or a breakdown voltage because of the stress and the heat induced in the material. Sometimes you'll see that contacts are made out of copper or silver because of their high conductivity. Before, we talked about transformers being sized by the application, by the kVA, by the load. Breakers are exactly the same. You need to size them for the voltage and the amperage and the application, single phase versus three phase. So the key concepts to know before choosing your breaker are knowing the maximum voltage, because that will be your nominal value of the voltage, the current at which you want to interrupt the circuit, and the capability of the transformer or the breaker in this case. So you want to choose one that will give you operation at certain temperatures and operation under certain loads, spikes of loads, and there are different types of breakers that you can choose for your application. The main thing I want to mention is learn how to connect them. Remember, the contacting and the connecting part is crucial, so you connect them by screws. Never operate, install, uninstall breakers if the panel board is not completely off. Is meaning if there's power going to the panel board, never try to switch a breaker. Make sure that the panel board has no power going into it. This is by the tag out standard. You can make sure that it's not powered. And once you choose your breaker, you would have a coworker or your manager or somebody else check for you. Usually you have multiple people, minimum two. One will do the tag or the um, will be shutting down the panel board or doing the tag out, and another person would be working on the panel on the breaker box. This is to make sure that the same person is not doing everything to avoid errors and mistakes and accidents. So one person will have the responsibility of making sure that there's no power going into the breaker box or the panel board, and the other person will verify that there's no power and will do the swapping, or usually a certified person will do the maintenance or swapping of components. And then when everything is connected properly, the other person would be checking that the connections are okay, and they take out the tag out and bring the panel board back to operation. As we said, there are different types of breaker boxes. There are two connections, one connection, two lead. So this one will be for L1 and L2. There are breakers where only L1 is going and L2 is still connected. So there are different types. This one will be the 30 amp breaker. You're still having a breaker like we mentioned before, with a casing that is made of dielectric or insulating material. And you will have other ratings such as the maximum voltage, as we mentioned before. So you can have very, very large breaker boxes, and this is something that say Toyota power plant, or not, I'm sorry, a Toyota manufacturing plant or a power plant using high amount of voltage and high values of current would have dedicated breaker units for their circuits. And there are switchboards that are the size of a room. This is also for a power plant, for instance, will use a large amount of electricity. A nuclear power plant would use huge switchboards to control the whole system. So, as I said before, they could be the size of a book cover, or they could be the size of a room. Usually, they will give you, within the more advanced systems, they will give you actuators and displays of the things going inside the panel board, the kilowatts hours, the kVA, the amperage, etc. That could be something that is usually able to be something that is displayed some point within the panel board or around, like in your house. You have this type of meters to show you your power levels. So always follow the installation rules and codes, safety and operational codes. Always make sure that the panel board is accessible. Don't put ladders or buckets or other equipment covering the panel board, because A, you have to provide maintenance, and B, that's a main way of shutting down the power for the rest of the system. So make sure they're accessible and they're always under good conditions.